This video will outline the concepts of power and efficiency and round off our learning about energy and energy conservation. So the purpose of this presentation is to define power as the rate at which work is being done or the rate at which energy is being transferred, to derive an expression for power in terms of force and velocity, and to define the efficiency as the ratio of useful power output to total power input. Okay, so firstly, to get a concept of what power is, if we look at these two cars, they can both reach a speed of 100 kilometers per hour. The second car, however, is capable of reaching this speed in a much shorter time. It has a more powerful engine. So what that means basically is that the second car is able to transfer kinetic energy to the car at a greater rate. Alright, so the average power output is defined as the rate at which work is done. So that's this first equation here. This is the work done divided by the time taken. The second equation is an alternative for the same thing. We know that the work done is equivalent to the change in energy of an object. And so the power can also be expressed as the change in energy of an object divided by the time taken for that change to take place. The average power of a process is the total work that we've done divided by the total time taken. The instantaneous power, so the power at a moment, is just the rate at which the work is being done at that particular time. Okay, so if we look here at an example, a student of mass 65 kilograms walks up a flight of stairs, gaining the total height of 5 meters. It takes him 4.2 seconds. Find the useful average power output of the student. So we have power is equal to work done over time taken. Work done is equal to change in energy. And so in this case, change in potential energy is equal to mg delta H, which is 65 times 9.81 times 5.0, which is equal to 3,188. 0.25 joules, and so the power is equal to 3188.25 divided by the time taken, which was 4.2, which is 759. And power, was it 759? Yes, it was. Joules per second. It's joules per second because we're dividing an energy by a time. However, we do have a unit that we replace joules per second with for power, or 759 watts. That's watts. And that's the standard unit for power. 2. Another student of the same mass runs up the stairs in 2.3 seconds. What's her power output? Well, her power output is she's going to gain the same energy, 3188.25, but she gains that in just 2.3 seconds. So 3188.25 divided by 2.3 is 1386. Watts. Everything should really be to two significant figures. So this should be 7.6 times 10 to the 2 watts. and this is 1.4 times 10 to the 3 watts. Okay, so that's how we can apply this power equation. For an object that's moving, the power produced we can derive a second equation for it. Work is given by the expression work is equal to force times displacement, where force is there the component of the force in the direction of the displacement, and power is given by work divided by change in time. So we can say work is equal to I'll go back to the power equation. Power is equal to work done over time taken, and the work done is equal to the force times the displacement divided by the time taken. But if we have a constant, so if the force is constant, then the power at a given time, at a given moment, is power is equal to the force times S over T, which is force times velocity, or force times speed. So for objects that are moving, if we know the force applied and we know its speed at a given moment, then we can work out the power of that object. So let's have a look at an example here. So the power delivered by an elevator motor. So we have an elevator of mass 1,000 kilograms carrying a maximum load of 800 kilograms. So we have an elevator like this, and its total mass is 1,800 kilograms. A constant frictional force of 4,000 newtons opposes its motion upwards. So we have a downwards force of 4,000 newtons. What must be the minimum power delivered by the motor to lift the elevator at a constant speed of 3 meters per second? Okay, we know that to move it at a constant speed, we're going to need a force of 4,000 newtons. So F equals 4,000 newtons, and the speed is 3 meters per second, and the power is equal to the force times the speed, which is just 4,000 times 3, which is 12,000, or 1.2 times 10 to the 4 watts. Okay, so the motor needs to supply the tension force in this example. So this tension force, and we know that the tension force must be 4,000 newtons because it's moving at a constant speed. So the power delivered by the motor must be 12,000 watts throughout this motion, throughout that 3 meter per second motion. Okay, the final concept in this topic is efficiency. And efficiency is just a way of accounting for the fact that some energy is lost. So not all of the energy that we put in do we get out as useful energy. So the efficiency of an energy transfer allows us to quantify how much useful energy we get out for every joule of energy we put in. So we just take the ratio of useful energy output here, and we divide it by the total energy that we put in. Or we can take or we can take the useful power output and divide that by the total power input. That should give us the same number, the same efficiency. And because we're dividing an energy by an energy, or a power by a power, we end up with no units for efficiency. It just is a number that tells us what proportion of the energy that we put in we get out. So a quick example of that: if we apply a 200 Newton force horizontally to a cardboard box full of books on the floor, which has a mass of 12 kilograms, while the force is being applied, the box moves a distance 1.5 meters and accelerates to a speed of 5 meters per second. So let's first find the work done on the box and then find the efficiency of the process, if the useful energy out is the kinetic energy. So So for the first part, work is equal to force times distance, which is equal to 200 times 5. No, how far do we move? 1.5. So that's equal to 300 joules. The second part here is to find the efficiency of the process. Well, the useful energy out is kinetic energy and the total energy in is 300 joules. So how much kinetic energy did it gain? EK is equal to 1/2 mv squared, which is 1/2 times the mass was 12 kilograms and the final speed was 5. So we go 0.5 times 12 times 5 squared gives us 10,500. Oops, that's it. I said 35. That's not right. Try that again. 0.5 times 12 times 5 squared gives us 150. So efficiency is equal to useful energy out over total energy in, which is 150 over 300, which is 0.5. So that's the efficiency. And it has no unit. We should really give it to 2 significant figures. Okay, so power is defined as the rate at which work is being done on an object, or the rate at which energy is transferred. And we have these 2 equations for power. It's measured in watts. The power at a given time can be defined as the product of the force applied and the velocity of the object. The efficiency of a process is the ratio of the useful power output to the total energy input. So useful, I should say, energy output to the total energy input. And you can replace both of those energies with power and you'll get the same number.